Hello, everybody. This is Darrell Lee Berry Jr. I'll be doing some experimental physics reading. I'm doing a lab experiment now. I'll tell you about it in a moment. Before that, be sure to like and subscribe if you haven't. You're on my Discord server. I'm on there now. I'll be sharing from my Discord server. And I also have my X link there, my Patreon there. So be sure to sign up to all of those. Now, right now, I'm taking an experimental physics laboratory. At least a modern physics laboratory. So we're doing experimental physics. And so basically what I'm going to do is we're working on the Frank-Hertz lab right now, experiment. So there's basically a list of experiments. We could pick which one we want to do. Me and my lab partner picked this one next. We measured the speed of light last week. So this week we're doing this. So what I'm going to do is read through one of the papers that came with the experiment because basically one experiment we do a oral report on. So this is the one I'll be doing my oral report on. So I do need to make sure I understand it well. It would have been nice to do one on the speed of light because I thought that was so fun to be able to measure a a constant of the universe, such an important aspect of not only physics but astronomy, which is my my favorite science, astronomy, astrophysics. So measuring the speed of light was real fun. I'll make a video about that, maybe a presentation about that and talk about that. Um, However, for now, the experiment of the day is the Frank-Hertz experiment. And be reading this paper here, which I'm sure is available online in various places. And let me make sure this is showing properly. There we go. Looks like, oh, no. Let's see here. All right, so it looks like that's showing now. Awesome. So I'll be reading this paper. I'll be going through it. And so basically to give you some background, and one thing that I find pretty interesting about this experiment is actually one of the evidences for the quantum reality of the universe. So the idea is that, and this is a rough idea, I'm still getting the full understanding of the details myself, but we actually gathered data with the experiment today and yesterday, and we had to, of course, read and understand the experiment. And our professor was really good about asking us questions about the experiment, making us think about it, making sure we understand what's going on. So the idea is that we have a tube that has either some mercury or some neon in it. The mercury we actually have to heat up into a gaseous state. And what we do is we send some voltage through it. And what happens is the voltage is actually accelerating electrons. So you send some voltage through to accelerate some electrons through the gas. And what happens is, on the quantum level, the electrons around the atom of the element could only absorb energy at certain frequencies. So they could absorb energy in the form of photons or light. They could also absorb energy in terms of collisions, but still, they generally absorb energy readily at a certain frequency where they could actually absorb that energy and release that energy as a photon. So what happens is, and what I read about today, talking with my lab partner and confirmed with my professor, what happens is that as we start to increase the amount of voltage, initially the electron has elastic collisions with the atom, which means that a whole stream of electrons are being shut out. But an elastic collision means that the electron hits the atom and bounces off and doesn't lose any velocity. It's almost like a perfect reflection, like a pool table ball or billiard ball that just bounces off perfectly, doesn't lose any speed. And the atom is so much bigger than the electron, it's not really affected either. So basically, it's like a perfect bounce. But what happens is that's the energy in the electron increases and it starts to go faster and faster, hit the molecule harder. There's a certain point at which the collision becomes inelastic. meaning that it loses energy when it hits the atom. So what happens is there's a peak in the elastic collisions. And when the elastic collisions are happening, the electrons are bouncing off and hitting a receptor. So it's a very strong peak. But then when the inelastic collisions start, the electrons lose energy after they hit uh, the atom. And then the amount that's hitting the sensor decreases, so the peak goes down. But as you continue increasing the voltage, they start to speed up again. And then they start building up elastic collisions again, and then the same thing happens, and then it goes down. An interesting thing about the neon one is when you do the experiment with neon, when the collisions are at the peak of elasticity and has enough energy to absorb at that proper frequency to emit a photon, you can actually see a glow in the sort of little window they have. As a matter of fact, I actually have a picture of it. I like taking pictures of my lab experiments, and well, actually, I'll show it on the outro. So it's on the intro, where you can see the little circular image, and there's three little lights. The professor was letting us know and confirming that what happens when as the electron has the elastic collisions and the as it starts to become more and more energy, some of that energy is absorbed and reflected as photons that we can see. It's just that with mercury, the frequency at which it emits light, we can't see it visibly, but the neon we can. And then when it reaches that peak, the energy starts to go down and then it starts to build back up again. And what happens is the same electron can excite uh, molecules farther down the line. So basically, the electron comes in, it excites some molecules. Eventually, the inelastic collisions start, so it loses energy. But then the voltage is strong enough where it pushes it fast again. It starts hitting molecules fast enough again to excite them, and it makes a second band of light. But then it starts to become inelastic because it's losing energy, depositing it into the atom. But then the voltage still increases again, so it could accelerate a third time and hits a third line of molecules. So each peak is basically a wave or a line of photon emissions after the energy is transferred into the atom. The electron loses that energy because it's inelastic. And then when the atom absorbs that energy, eventually that electron in its orbit that absorbs that energy drops back down the state and releases that energy, and we see that emission. So very quick explanation. There's probably some details I can clarify up in there, but what I think I'll do this semester is every single experiment, I'll do a presentation on it. So I'll take pictures of all the experiments, and I'll do a presentation. But for now, I'll go ahead and read through this article. As you can see, it's 5 pages. And let's see if I maximize this, what happens. Okay, it's best to keep it minimized. All right, so I'll go ahead and start reading through this. And if anybody joins, you could join in the chat, the live chat and ask questions. You could also join in the Discord. So I'll be sitting in a Discord like so in the main chat live stream section. And so any chats you can go ahead and put up in there. And here we go. What really happens in the Frank-Hertz experiment with mercury? This paper is from 1987 by G.F. Hayne. Recent studies using spin-polarized electrons have revealed the role that various interactions play in inelastic collisions of slow electrons with complex atoms. It has been shown that electron exchange and resonances, the temporarily negative compound ion states, strongly influence the excitation cross-sections of the first excited states of mercury very close to excitation thresholds. The particular result attained in the Frank-Hertz experiment is determined by the magnitude of the excitation cross-sections involved and depends on the geometric design of the tube. So that's not very clear to me now, but hopefully it will as I read through the paper. So I'll call my little file where I'm taking notes at what really happens. Right, so introduction, the electron-mercury collision experiment of Frank and Hertz, for which they won the Nobel Prize. So, thought perhaps they won the Nobel Prize, but they won the Nobel Prize in 1925. That's awesome. No wonder why we is a regular part of the undergraduate physics, modern physics laboratory. So one of the key experiments they help establish atomic theory. So when I pause, I'll be making notes. It shows that atoms can absorb energy only in quantum portions conforming to Bohr's postulates. So I believe that's called quanta, specific energy levels, right? So atoms can only absorb energy in quantum portions, or quanta, conforming to Bohr's postulates. Due to its simplicity and the clear-cut experimental result, okay, which facilitated its explanation by Frank and Hertz. It is often demonstrated in classes and cited in most textbooks of modern physics. So I could have actually called this talk a modern physics as well, but since I'm not specifically reading from that book, I called it experimental physics. So classic in modern physics. And this will help me with my understanding of quantum as well, because I'll be taking a quantum class in the fall. However, this experiment will not show such clear-cut results if there were not special circumstances, which have been revealed only very recently by studies using modern experimental and theoretical techniques. So interestingly, there's some things about the experiment that were not even clear at the time. So I guess it was almost a sort of luck that they stumbled upon what they stumbled upon. Right? The purpose of the present article is to review and interpret some of these recent studies and to show that the Frank-Hertz experiment contains much more interesting collision physics than is usually assumed. A real understanding of the outcome of this apparently simple experiment requires a detailed knowledge of the basic collision processes by which it is governed. All right, so I guess they're going to be going into this, uh, the underlying uh, idea behind how and why it works. Right. So first it gives the textbook explanation, the FH curve, figure one, and let's see figure one. Okay. So they're talking about this curve right here. And by the way, this is what our data looks like. When I give my presentation on it, I shall share uh, some of the data, how it looks from our graphs. But this is what the data looks like. The data from uh, the device that records the excitations of the atom and the drop-offs. So is my mouse showing? Looks like my mouse isn't showing. I might have to save a setting. We're looking at the graph B on the right with the sort of waves going up. The top of the wave is right where elastic collisions are maximum, and then it starts to turn over into inelastic collisions, which means fewer electrons make it through. And then the same thing happens again and again. It just seems interesting. It must mean since, like for instance, with neon, we see 3 rows of lights. That means that each time it is still exciting. Is literally the electrons that's coming from the emitter is literally exciting 3 rows of electrons of atoms every single time. That's quite interesting. Figure 1 shows a schematic diagram of a tube with which the experiment is usually performed and the result of the experiment. Electrons are emitted from a cathode with nearly zero kinetic energy. Okay. They gain kinetic energy in traveling toward the control grid, which is positive relative to the cathode by U volts. Okay. So I thought they were actually being shot, but then really being pulled towards the control grid by electrostatic force, I imagine it could be called. In transit, they collide with mercury atoms in the tube and lose energy. Okay. Electrons that reach the grid with kinetic energy of 1.5 electron volts or more will be able to reach the anode and be included in the measured current IE. Okay. All right. So some of the uh, electrons lose energy and don't make it as the voltage that's pushing them increases. Only the ones with at least 1.5 electron volts of energy will be able to reach the anode on the other side, and only those that reach the other side are included in the recording. Now it says that electrons with less than 1.5 electron volts. So let me think about this. Traveling toward the control grid. So the control grid is on one side and it's positive, and it's pulling the electrons to it. So first they reach the grid, then they reach the anode. So they report it at the anode. those with less than 1.5 electron volts at the control grid don't continue to the anode. And they fall back. Oh, I see. Fall back to control grid. So the electrons are being pulled towards the grid, go through the grid, and either they have enough energy to keep going or they don't, and they get pulled back like light next to a black hole, basically. These are not included in the measurement I current. Okay? Now, if we look at the graph on the right, B, we see that the x-axis is the current, and the y-axis, excuse me, the x-axis is the voltage, and the y-axis, the x-axis is the voltage, and the y-axis is the current. And it looks like the difference between peaks is going to be about 4.9 volts, which is about what we got in our experiment. We got about 5, which is within our error. Within our error, 5 electron volts uh, is the actual amount within our error. So that means that as the current increases, because the bottom line, the current is actually one of the, so basically two of the circuits had a steady current, but the one in the middle was able to be increased, and it was steadily increasing. So as it was increased, it allowed it to hit uh, go through stronger, and more of them got through because more of them have more energy. If that makes sense. So it seems that some, even though overall more of them get more energy, some of them still have less energy and still excite the first one. And let me check and see if anybody joined the Discord, right? Frank-Hertz originally thought that the peak spacing in the curve they obtained had to do with the ionization potential of mercury, but later they gave the correct explanation, which in the modern textbook reads, okay, so this will be important. And I'm right here. The peaks are occurring at a spacing of about 4.9 electron volts. The first dip corresponds to electrons that lose all their kinetic energy after one elastic collision with a mercury atom, which is then left in an excited state. So basically, an electron is going through, it hits an electron, excuse me, an atom, it loses its energy, and then it sort of falls down, you can say, and that becomes a trough. So how do I write this? I'll say the peak is electrons having elastic collisions and continuing through control grid and to the anode. And the trough is when electrons have inelastic collisions, deposit, I'll put deposit in quotes, energy into atom and fall off. So that would mean that the excitation is, that means that the area of the grid that's emitting photons is during the trough, because that's the area where the electrons are losing energy and depositing it, and then it's peaking. So that's interesting. The second dip corresponds to those electrons that suffer two inelastic collisions with two mercury atoms, losing all their kinetic energy and so on. So this is one first collision, second collision at each lump, third collision. All right. The excited mercury atoms return to their ground state by emission of a photon, as I was saying earlier, according to according to mercury to mercury plus Hv, but Hv equals E2 minus E1. And we know that E equals Hv, so that deals with energy becoming a wavelength. So it reminds me of what? It reminds me of chemistry and the photoelectric effect. When you're talking about how much energy does it take to knock off an electron from a metal with the photoelectric effect, usually as E is Hv. From spectroscopic evidence, we know that mercury vapor, when excited, emits radiation whose wavelength, so I'll put this here, the wavelength of excitation of mercury is 2536 angstroms. And a photon energy of 4.89 electron volts. All right. Radiation of this wavelength is observed coming from the mercury vapor during the passage of the electron beam through the vapor. So while the electron beam is passing through the mercury, we see emissions in the 2536 angstrom wavelength range, given the photon energy, and the photon that is equivalent to that wavelength is 4.89, or there you go, your 4.9 electron volts, which again is what we saw given our experimental error. Radiation of this, okay, so the simple explanation is correct in principle. So I don't think I remember seeing what they said incorrectly. But ionization potential, it is mentioned as a one-liner. So ionization potential is wrong. That's the original Frank-Hertz explanation. But eventually they got it. So it deserved their Nobel Prize and then some. This simple explanation is correct in principle. However, a deeper insight into the problem raises two questions. Is the observed energy loss the result of simple inelastic collisions? And why is the energy loss about 4.9 electron volts? The first excited state in mercury corresponds to an energy loss of 4.67 electron volts, as indicated in figure 2. So let's check out figure 2. So this is literally the energy states. I remember this from chemistry. I wasn't so good at it, but I had to get basically good at it to pass my chemistry class. So physics majors are required to take chemistry, and you understand, you can see why at this point, right? Astronomy as well, you need it. And it's for the same reason you're dealing with spectra, which is the emission of photons from atoms that absorb energy at certain quantum level state what values. So it's very important. And this is a simplified energy scheme of the lower states of Mercury, which is a simplified energy scheme of the first excited states of Mercury, in which the hyperfine structure, due to nuclear spin, has been neglected. The hyperfine does ring a bell when it comes to time. The second, the SI unit of time, the second is actually measured by how long it takes for a certain hyperfine transition of a certain atom. I think the atom is CS. So currently there's these, I don't understand hyperfine fully, so I'm gonna have to look into that hyperfine. I'll put a question mark there. These questions will be discussed, and it will be shown that the observed peak separation depends on the geometry of the tube and the Hg vapor pressure, and is mainly but not solely related to the 4.89 electron volt transition. So there's a few things at play. Observed peak separation. And when they say observed peak separation, I'm sure they mean how much distance and voltage is between the peaks in the graph. So it depends on geometry of the tube, the Hg vapor pressure. Hg is mercury, the atomic name. And related to the 4.89 transition, electron volt transition. Thus, students and instructors should not worry about results that show a peak spacing in the Frank-Hertz curve that deviates from 4.89 volts by a few tenths of a volt. There you go. So we got 5 electron volts, which is 1/10 of a volt. Is very good. So deviations by a tenth are not bad. Electron exchange is a significant excitation mechanism, right? So that was the introduction. Well, introduction in section 2. So what I'll do, I'll actually come back and finish reading this tomorrow. So I see it's getting a bit late. Got a good 35 minutes in, wanted to get it started. I took some time getting all the details of the stream set up, so it took me some time as well. So I'll go ahead and take a break. Everything is all set up now, so I should be able to come in tomorrow and just jump right in and get started. Make sure you like and subscribe. Make sure you join my Discord. My other links are there as well, my X, my Patreon. And hopefully I'll see some of you all tomorrow, either in the chat or in the Discord. We can have some more science discussion.